Good afternoon, everyone. I'm Miho Yamauchi. Let me start the 20th I2CNER seminar series. It's my great pleasure to introduce today's lecturer, Professor Kenichi Aika. Aika is a very famous professor for industrial ammonia synthesis. He graduated Tokyo Institute of Technology in 1964, and he had various experience as a postdoctoral fellow in USA, such as Princeton University, and the provision of Professor Takevich is very famous professor for the gold synthesis using citric acid. Then, after the postdoctoral fellow in Texas A&M University, and then he moved to Tokyo Institute of Technology as an associate professor, and then he became a full professor in the same university, Tokyo Tech. Then he studied the study of the ammonia synthesis catalysis, and now he retired at Tokyo Institute of Technology. But his activity, he is still active scientist as a program director, sub-program director of energy carrier of Cross-ministerial, such as NICAC is very important person for the our the future vision of the energy sciences. So today he will give us a talk about ammonia synthesis on iron and ruthenium catalysis, laboratory to industry. So we can learn many things about the industrial ammonia catalyst. Let's start.
Thank you, Professor Yamauchi, to invite me to this Kyushu University. This may be my third time to visit here. This 2 years, every year I visit here in March or February. Probably the Catalyst Society of Japan was held here 2 years ago. And last year I visited Professor Matsumoto's laboratory and Ishara's laboratory as a site visit of the program. Now I'm engaged in a large energy carrier program of the government, and I'm very happy to cooperate with all the researchers associated with energy carrier research in Japan. But today I would like to speak very old science and technology, but I think it's very important because now the ammonia synthesis is kind of completed technology, but it contains a lot of fruitful science and technology is hidden in the industry and of course the academic world. So my message to you is learning old makes something new. This may be some old Chinese proverbs, but this kind of science is many inside the industry. So my lecture is a little bit, say, a kind of tutorial lecture for you, but I think this may help you something. as you know, ammonia is known as a fertilizer or chemicals, or of course refrigerant fluid or dinox agent. But in the future, I would like to say ammonia must be used as an energy carrier or fuel for fuel cell or fuels for power plant. My talk will be shown like this. First, I would like to talk about the iron catalyst for ammonia synthesis, then ruthenium catalyst, and at last I go to some industrial application for this process. As you know, ammonia synthesis is people called ammonia consume a lot of energy because the reaction is going on at high temperature and high pressure. But I would say that is not correct. This condition is necessary for equilibrium condition. Ammonia synthesis is like this. One molecule of nitrogen reacts with 3 molecules of hydrogen to make 2 molecules of ammonia. So molecule decreasing reaction. So this is exothermic. At high pressure, the equilibrium is high, and this produces some energy, heat. So at lower temperature, the conversion is high. So usually in industrially, about 350 degrees centigrade and probably 10 megapascal or 20 megapascal of total pressure is used. But if the temperature is so low, the reaction rate is low because the nitrogen dissociation is very hard process. Hydrogen dissociation is rather easy, but nitrogen, as you know, have a triple bond. So this is a rate determining step of this reaction. The other reaction is rather easy. Hydrogen is split quite easily, and hydrogen and nitrogen combine quite easily to produce ammonia. The most problem is nitrogen rupture, nitrogen bond rupture. This is a modern process. First, we learn the ammonia synthesis energy aspect. So this is a modern ammonia process, probably done under the Kellogg company. And the most modern ammonia process use methane, natural gas, as a energy source. And this reacts with water for steam reforming to produce CO and hydrogen. But meanwhile, the air, nitrogen and oxygen is added to these molecules. So this is a secondary reforming process to produce CO, CO2, water, hydrogen. But the shift reaction converts CO2 completely to CO2. And the water is eliminated. Then these 3 molecules is going to this process to eliminate carbon dioxide, and nitrogen and hydrogen is reacted with inside the reactor. So interestingly, air is used as an oxidant. So this contains nitrogen, and the nitrogen and this hydrogen is quite well balanced to give 1:3 ratio of nitrogen and hydrogen reactant gas molecules. And this makes some ammonia and refrigerated and separated out, and the rest gas warmed it up and compressed and recycled like this. So the process is rather simple. No carbon contaminant because some FCO is converted as to methane and to evaporated at time by time. So let's take a look at the reaction. So ammonia synthesis, the hydrogen source comes from methane and water. And first, this reaction to produce hydrogen, this is a endothermic reaction. But at the same time, we need some oxidation of methane, complete oxidation of methane by air. So this reaction is exothermic. And hydrogen and nitrogen are used as a reactant. So this and this and this three reaction is multiplied to give this formula. So 7/18 methane to give one molecule of ammonia. Interestingly, this reaction gives quite a small amount of exothermic resultant heat. So this is almost negligible of the ammonia combustion energy. So in other words, the material balance is like this, and heat balance is almost zero. So this is very interesting process. So almost zero heat balance, that means energy of natural gas is transferred to ammonia. So to consider the ammonia synthesis, it's very easy to think about the energy transfer situation. So, for example, methane may have some 23rd gigajoule per ton of ammonia go to 22.5 gigajoule of methane, ammonia. So this is a combustion energy of ammonia. But actually, we need some energy loss, about 11 or 15 gigajoule. So most of the methane energy transfer to ammonia. And usually, it is pity most of the chemists think ammonia synthesis consumes a lot of energy. Of course, ammonia synthesis consumes almost 1.5 energy of the world. But that is not consumed. That is converted to ammonia. So ammonia accepts the energy. Of course, this is used for fertilizer, but in the future, this must be used as a fuel. Now, let's think how we can produce ammonia from water and air. So, in this case, we may use water as a hydrogen source. This is an endothermic reaction. And ammonia synthesis use separate nitrogen from air and hydrogen from water. This is an exothermic reaction. The two reaction gives like this. So this is just the reverse reaction is just like the ammonia combustion. So the reverse reaction of ammonia combustion is ammonia synthesis from air and water. So the theoretical energy is just like ammonia combustion energy. In this situation, in order to get one ton of ammonia, we need some electricity a little bit higher than this level, but almost the same as this level. Of course, electrolyze of water, theoretically 1.2 electron volt, but it maybe takes some extra energy, 1.8 volt or 2 volt. But the situation is just like this. So in the future, we can control this process for the future. But today, I tell you about this process, this the secret of the energy loss system. The 11 gigajoule of energy loss contains hydrogen production and ammonia synthesis process. And hydrogen production needs some heat up and energy lost. So it was a hard process, reforming or shift reaction. So we may lose some energy like this. And ammonia synthesis loop just lose 4 gigajoule or very small. So this is a result of technology of catalyst and the process. So when we take a look at the history of ammonia synthesis process started at the end of 20th century. Before that, something plasma reaction or calcium cyanide process is used. But Harvard Bosch invented the ammonia process catalyst. The energy, at that time, the energy may be over 100 gigajoule per ton to produce per ton of ammonia. But the process techniques and the catalyst techniques was developed a lot, and the energy consumed going down little by little. And finally, at present, we are enjoying the 35 or so. But this is a theoretical limit. This is the energy of ammonia itself. It is interesting to see 1942, the Belgian bus used ammonia as a fuel. This is an ammonia tank, and as a starter, some coal gas is used. But this bus ran 1 year. And this is a US ammonia truck, and this is an Italian ammonia motor car, but the car itself is Toyota's. And Hyundai is also developing some ammonia car. So ammonia can be used as a fuel. So, and before going to the science, I select one slide from the commercial print from Yara. This is the world's largest company to sell ammonia. They say ammonia is used as a fertilizer that may lose a lot of natural gas in the world, but they say if this is used as a fertilizer, this can give some foods or biomass, and the energy of this may be 5 or 10 times more. So this is a theory from Yara. So I don't know if this is correct or not, but anyhow, the ammonia, if used as a fertilizer, this helps to fix CO2. So now we go to some science. As I told you first, ammonia synthesis, nitrogen dissociation is the hardest process. So first, dinitrogen react with ammonia to give two nitrogen atoms. This is a rate determining step. If we consider this rate as K, and the other reaction is quite easy. So the nitrogen absorbed react immediately with dihydrogen to give ammonia to leave one side of active site. So this is in equilibrium. The equilibrium constant may be written as 1 by K. So the reaction rate theory gives like this. Rate of ammonia production is linearly related with the pressure of dinitrogen and inversely related with ammonia pressure and linearly a little bit highly orderly related with hydrogen. So this is a Langmuir type reaction rate. So if we design the catalyst, what kind of element, what kind of catalyst we must select? Say that if K is fast, the reaction rate is fast. And if K is small, the reaction rate is fast. So when we choose some transition metals as a catalyst, the absorption energy of nitrogen is rather important. If some metal absorb nitrogen quite strongly, and at the same time, the equilibrium of this may be strong. So if both is the favorite one is this combination. But if some metal absorb nitrogen quite strongly, the rate is rather low because this is quite large. But at the other end, nitrogen is quite weakly absorbed. K is rather low. So the element which is rather intermediate absorption strain is favored. So this is an experimental result. This is not absorption of nitrogen strength, but instead I put it as a oxygen metal bond strength. So this is rather linearly related with metal nitrogen bond strength. So rhenium or molybdenum of these metals absorb nitrogen quite strongly. These are not good catalysts. But at the other end, platinum absorb nitrogen weak. This is not good. So intermediate molecule elements, ruthenium, cobalt, or iron, is a good catalyst because these elements absorb nitrogen rather intermediate in strength. So if we take a look of the periodic table, those elements is some character which have, say, a kind of nitride, metallic nitride. But in normal condition, those late transition metals cannot make any nitride. But early transition elements can make some nitride. So those intermediate elements are good catalysts. So iron is should be a good, very good catalyst. But the story is not so simple. Most of the surface scientists study iron a lot in every aspect. Mostly the surface science studied iron for ammonia synthesis quite much. And the famous scientist Yamauchi, University of Berkeley, and their group found that iron of 111 surface triangle structure is extraordinarily active for ammonia synthesis than 100 square or 11 or these plane rather less active. So ammonia synthesis is quite sensitive to the surface structure. So this is a second problem. And Professor Arthur, he got the Nobel Prize. Studied also a lot of surface science study, and their model is iron 111 structure favor dinitrogen like this, and this structure may pull from the other side to keep nitrogen atoms. So for ammonia synthesis, iron may be quite good to pull these dinitrogen absorbed state from both sides to give nitrogen atom like this. So probably on iron surface, this process may be the slowest step. And later I pointed out the ruthenium may be important to this step. And in old days, the surface scientists distinguished three types of nitrogen absorbed state. The quite strongly absorbed one is atomic state. They called beta type. And this called as alpha type, and this called as gamma type. This is most weakly absorbed. And if the iron have some structural sensitivity, most of the surface science study is done under the atmospheric pressure and normal temperature. But at higher temperature, the surface might change. So this condition, we wonder this condition is not kept. And indeed it was so. But why the industrial iron catalyst is active under this condition? This is the next problem of our study. I started my research career late 60s, in very old days. At that time, I studied a lot of pure metal as a catalyst. And of course, I studied ammonia synthesis of pure iron a lot. And this is not a main result of this research, but this picture is given in the experimental section. And usually we never put some result in the experimental section. But I was very in trouble at that time to get a steady state reaction rate to use the ion catalyst. So in any condition, the steady state was not attained, but just after the ammonia synthesis, the reaction rate got stable. So, and I checked some isotope work under these conditions, but in the experimental part, I rather used this experimental result, how I was in trouble for these 2 weeks or a month. And probably the surface may be changed. And later we found the reaction intermediate might cultivate the surface to give a good condition for ammonia synthesis. And of course, iron is not so strong. The melting point is not so high. And the surface is rather fragile at high temperature. And this might make some nitride. So we can imagine iron surface may be changed during the reaction. And after our findings, some French researchers, Amarigulio or their co-workers, did a similar result. They tried to get some steady state of ammonia synthesis under iron particles when they change the nitrogen content or activation temperature or the reaction rate of ammonia synthesis as a preliminary pretreatment. So if they use pure nitrogen, the activity is quite low. If they put pure hydrogen, the activity is low. If they treat nitrogen and hydrogen as a conditioning gases, the activity gets steady. So the ammonia synthesis, in order to get the steady state, ammonia synthesis reaction itself was important. So that was their findings. And after that, the Samurai, the surface scientist, tried to check the effect of alumina. They used iron 111 surface, the black, the 1O surface, the activity is low, 110 quite low. But if they add alumina on their surface and treat it with water, the activity of even the activity of 100 surface become large. 110 surface become large. So this looks like even those surface might change to 111 surface. So the surface was changed. This is their mechanism. The less active iron surface 110, if they add alumina and water, the iron gradually react with alumina to make those some mixed oxide, and if they treat this with nitrogen and hydrogen, they claim iron 111 surface is produced. I'm not sure this model is correct or not, but somehow iron surface became stabilized in addition when they added the alumina on their surface. So industrial catalyst is such a thing. usually, industrial ion catalyst is a combination of fused iron oxide and alumina, and sometimes added with calcium oxide or potassium oxide. But they reduced under ammonia synthesis condition for a long time. And iron and alumina mixture was produced. And iron is covered with alumina, but this condition gives iron as a quite active phase. So probably alumina has such a role to stabilize catalyst surface to keep ammonia activity high. So this is a result of the ammonia synthesis rate as a function of alumina. If they put alumina as a structural promoter, the activity going up. And of course, potassium makes some role, but potassium is some chemical promoter. The role of potassium is different, as I told you later. Now, iron, the simple metal iron itself has a lot of feature, but ruthenium is rather simple but different character. This is an ammonia synthesis and isotopic exchange reaction over ruthenium powder, just ruthenium powder. So ammonia synthesis, this and this. And this is promoted with addition of potassium vapor, just potassium vapor. The system is very simple. Ruthenium powder and potassium vapor. This combination increases the ammonia synthesis activity 100 times, and ammonia isotopic exchange reaction 1,000 times. So this is a reaction rate as a function of reciprocal temperature. This is so-called Arrhenius plot. So how potassium promotes ruthenium catalysis a lot. So this is our findings. And of course, every metal can be promoted with the addition of potassium, but ruthenium is extraordinarily promoted. And okay, the nitrogen is probably interact with transition metal as a linearly coordinated in shape. So the electron is donated with this, but the d orbital electron may be back donated to anti-bonding of the dinitrogen orbitals. So this may lose this bond. So most of the element has such a tendency, but in ruthenium, this effect looks like quite strong. So we prepared ruthenium catalyst on aluminum support and add small amount of potassium, in this case cesium oxide. The dinitrogen, IR spectrum dinitrogen can be observed. The end bond stretching have the, say, 2331 wave number. So most of the dinitrogen observed on these catalysts lose their strength 2200 or 2100, like this. So this means these promoter may donate electron to ruthenium and to activate dinitrogen. And interestingly, the extent of the rules of dinitrogen observed strength is related with the ammonia synthesis rate. So this catalyst is the most active. Ruthenium supported on magnesium, promoted with cesium oxide. This has some IR spectral dinitrogen molecules quite activated, like 2000 wave numbers. This has a quite high activity, 1000 micromole per gram catalyst level. But the other extreme is the alumina ruthenium system. This has not so activated dinitrogen in state, and at the same time the activity is quite low. So if ruthenium surface, the electron is donated from these promoters, the dinitrogen can be promoted. Probably in a short lifetime at high temperature, dinitrogen may be observed in linear on top state, gamma type state. But if once this is bonded to weaken, the reaction is going on this and this. So on ruthenium surface, this process looks like quite fast. So the activation of this process may be important. So this is a model of dinitrogen activation on ruthenium surface. So first we found potassium metal itself will donate electron, but cesium oxide itself also promote these catalysts a lot. So probably this state may donate electron to activate dinitrogen to give good catalyst. Ruthenium is usually prepared from ruthenium carbonyl, and the demo picture is like this, and some random ruthenium like this. But we skip this. Okay. When we evaluate the promoter, we use sometimes electronegativity of compounds. Usually electronegativity is used as a concept of the element. But if we apply this to the mixed oxide, for example, MgO, electronegativity of magnesium and electronegativity of oxygen is multiplied and square rooted. So this is a average of electronegativity of elements. So this is we learned this from the inorganic textbook of Sanderson. I'm wondering, this is rather famous in modern inorganic chemistry. But in old days, we used the electronegativity of compound a lot. And those criteria is rather useful to evaluate the activity of ammonia synthesis or ruthenium catalyst. So those are all promoter or support. So if material have less electronegativity, it gives more electron to ruthenium to activate dinitrogen alone. Barium oxide is also quite good promoter, and probably the industrial catalyst barium may be used. And the problem of barium is if we contain some water in this system, barium oxide turns to barium hydroxide, and in this case, the activity gets down. But if we eliminate water in this system, the barium hydroxide returns to barium oxide. In that case, activity of ammonia synthesis return to the same level. So those promoter is very fragile, but some making some intermediate stabilized state. So industrial catalyst may be in these conditions. This is a picture of electron microscope transparent electron microscopy taken by Topso or catalyst manufacturer. They claim those are barium on the surface of ruthenium. So if barium or barium oxide cover ruthenium, the activity got high and stabilized probably under the real commercial process. Now, the problem of ruthenium have a little bit different. Ruthenium is suffer from quite strong hydrogen inhibition. Interestingly, ruthenium observe hydrogen, and we observe two kinds of hydrogen from IR spectroscopy, and very small amount of hydrogen kick out the dinitrogen atoms. So hydrogen under ammonia synthesis, nitrogen and hydrogen is important, but hydrogen is an inhibitor of dinitrogen absorption side. So if we make commercial ammonia catalyst, this is rather important. For iron catalyst, hydrogen inhibition never, but nitrogen itself is an inhibitor, interestingly. So the reaction rate is shown like this form. Nitrogen is in linearly related, and hydrogen is a positive order, but ammonia is a negative order. That means if ammonia is produced a lot at the end of ammonia synthesis reactor, this state, nitrogen atom cover iron quite strongly. So no more ammonia is produced under the end, at the end of ammonia reactor. So iron catalyst is used just in front of the ammonia reactor. But ruthenium, ammonia inhibition is quite less, but hydrogen inhibition is some. So the kinetics is quite different. For example, we if we increase the pressure of synthesis gas, this catalyst, ruthenium, cesium, MgO system, the activity is getting down because of the high hydrogen inhibition. But ruthenium cellular system, hydrogen inhibition is rather less. So we can get 20 or 30 bar, the activity become high. But there are still some hydrogen inhibition. So ruthenium is such a thing, but in other words, we can develop a lot kind of catalyst choosing support or promoter. Okay, now the Kellogg company is selling a large-scale ammonia plant like this 10 years, and the heart of this process, they use iron in the catalyst in first stage, and ruthenium as the last 3 stage. So they are very clever. Iron is rather difficult to use more because ammonia inhibition occur at the later part. But ruthenium is safe. And so ruthenium can be used even if the ammonia produced more. So iron and ruthenium is rather neighboring position in the periodic table, but the character is quite different. And they even in the ruthenium systems, the character is quite different. So catalysis is such a thing. Quite recently, we must use renewable energy, and we may have some extra electricity from wind, and they can produce ammonia from hydrogen. This is a water electrolyzed product. This is a pamphlet of Proton company in the Netherlands. And this is a small-scale ammonia plant, hydrogen source of biomass. And now the new era has started. So we have a lot of we may have a lot of different technology of ammonia synthesis in the future. Of course, we are enjoying the large scale of ammonia process from natural gas, but in the future, we may have the different character of ammonia synthesis plant. So I might skip something a little bit, but my message through this lecture is catalysis has a lot of aspects, service science aspects, or catalyst managing aspects, or process aspects a lot. The resultant process, which should be used in the real industrial production, must be, looks like very complicated, but that in every technology has some meanings. So for the young people, I would say such kind of technology hidden in the old process is rather important. That is my message. Thank you.
Thank you so much for your very, very nice lecture for us for understanding of the basis of ammonia synthesis toward application. And your final message, very impressive for me. And so then we can receive questions from audience.
Thank you for basic and important talk. So I'd like to ask about ruthenium carrier catalyst. So why ruthenium support decrease the hydrogen inhibition?
At present, I have no answer. The problem of hydrogen is very important, but there are very few research. We started a little bit, but we have not done a lot because hydrogen, the observation of hydrogen is rather tough. It is rather hard to observe hydrogen through infrared spectroscopy or such and such. And also, the problem must be studied under high pressure of hydrogen. That is another problem. So those are your problem in the future.
Thank you very much.
Okay, one thing that may depend on some structure, surface structure. Hydrogen, there are several types of hydrogen, maybe on top type or bridges type or something. So bridge type may be quite strong, but if you choose some on top hydrogen, it's rather easy. That may be kicked out easier.
Thank you very much for very interesting talk. I have two questions. The first question is about so you mentioned that ruthenium is a best element for to absorb the nitrogen gas, but the ruthenium, even the ruthenium needs the promoter such as ruthenium hydroxide. So that means the ruthenium electron state of ruthenium is a little bit different from the optimized state. So my question is there any example of the metal alloy catalyst in the industrial use?
Yes. One of the active ammonia catalyst of binary element catalyst is molybdenum cobalt system. So that is not commercialized, but the molybdenum cobalt is some unique character, and that have some possibility to be commercialized.
So let me ask one question. What is the reason for this catalyst cannot be used?
Okay, iron, ruthenium, molybdenum, cobalt, those are very near neighbors in the periodic table. And if they combine each other, they may make some intermediate nature or some different structure. But the most important thing is, complicated one is how those are connected with the promoters. Those elements itself cannot be a real catalyst as a simple shape. They need some promoter or stabilizer. So the science of this combination must be in the future problem. So actually, we have also studied molybdenum cobalt system, but the system is very much complicated. The preparation techniques is very much complicated, and we cannot find the reason at present is not clear.
Let me ask the second question. The second question is about, so I also think the ammonia is a very promising chemical for the next generation fuel or the energy society. But do you think what kind of feature of the ammonia will be the problem for actual use? For example, I know that ammonia is very, very toxic and it smells. So, do you have any?
There may be a long story if I tell this, but now I'm engaged in the, some energy carrier program which covers liquid hydrogen and hydrogen, organic hydrogen, and ammonia. But the problem with ammonia may be some acceptability from the society, or say how to control if the accident happens, such and such. And in US, in these 10 years, every September they have ammonia fuel conferences, and about 50 people get together every year and discuss those problems. And of course, ammonia is at present used refrigerate fluid rather large scale. But in those systems, the system is completely closed. Of course, accident does not happen usually, but even if some leak occurred, they try to keep ammonia inside the system. So such and such. So if ammonia is used as a fuel, the ammonia can be controlled in industrial area or some power plant, not in-house. But in old days, every house have a refrigerator equipped with ammonia refrigeration system. So if the system is not so large, ammonia may be introduced in the house.
Thank you very much.
Thank you very much for this very interesting talk. And in nature, usually ammonia is produced by nitrogen fixating bacteria in very mild conditions. So there is a lot of research which is directed on mimicking the enzymatic reactions in bacteria and fixing nitrogen, thereby homogeneous catalysis and catalysis which resembles the enzymatic structure. So do you think, what you showed was industrial processes with surface science. So do you think the time will come soon, anytime soon, because so much research is in the area of homogeneous catalysis, that this homogeneous catalyst for ammonia for nitrogen fixations will replace iron and ruthenium in the industry?
There are two reasons I don't think so. One is the ammonia synthesis in biological system is down under atmospheric pressure and temperature. And under those conditions, the equilibrium amount of equilibrium percentage is not so high. So those systems consume a large amount of extra energy to regenerate the nitrogenase system on it. But interestingly, the science of active site may help to produce some industrial catalyst. So nitrogenase have some iron and molybdenum element as a corner. So those are quite resemble to the industrial iron element. So there may be some resemblance. So in some way, those two sciences may connect each other, but there are some long chain, I guess. So both sciences very important, but we cannot mimic nitrogenase to industrial production at present. That is my opinion.
Thank you very much.
I learned a lot for your presentation. Thank you very much. I have a question for Professor Aika. Please tell me how is the weak point of the ruthenium catalyst or in the ammonia synthesis?
Ruthenium
Weak point.
Weak point. Okay. Every catalyst may have some strong point and weak point, but as I told you, the most weak point may be hydrogen inhibition. So I hope the young audience, if they study ammonia synthesis in the future, especially ruthenium, please get rid of hydrogen cross ruthenium surface. So, and the observation of hydrogen on those surface, there's a less study.
Please, thank you.
Like a very interesting talk. Thank you very much. And I rather want to ask you on the details of your catalyst. On the page 51 slide, you show the effect of the additives and also the support oxide. And you show that the celia is very effective for decreasing the hydrogen inhibitions. And I want to know the reason why celia, especially according to this slide, heat treatment temperature is also effective to such kind of positive effect. So I want to know what is happening on the ruthenium celia, why the inhibition is decreased.
At present, I have no answer. There are some special conditions to get such state. Probably ruthenium titanium oxide may be strongly reduced. Probably titanium oxide may have some valency of titanium maybe between 3 and 4. So partly titanium oxide may be reduced and cover ruthenium surface. But we have no reason through the measurement. But we imagine titanium oxide may have some special covering of ruthenium.
So this effect is so-called strong metal support interactions.
Right.
Therefore, is this sometimes recovery after exposed to the oxygen treatment?
But at present, including our groups, there are rather less information of such chemistry. So in these days, I'm very happy many people got some interest of the ammonia catalysis. So I hope such science should be solved in the future.
Okay, thank you very much.
thank you very much, and I'm very interested in the effect of support and promoter. You showed us very large improvement of catalytic activity by changing the support material and also adding the promoter compounds materials. And on the other hand, I'm working on the solid oxide fuel cell and solid oxide electrolysis cell. And in that case, electrodes are a kind of catalyst. It is sometimes called electrocatalyst. But in that case, we are not so doing such effort in tuning the electrode materials or compounds. Or in your case, your electrodes are very complicated, support the catalyst and also promoter. So I think if we make some such kind of effort for the SOEC electrodes or SOFC electrodes, we can improve the catalytic activity or electrocatalytic activity of the electrodes. Do you have any suggestions or comments for the solid oxide fuel cell people or solid oxide fuel cell research?
Thank you for your comment. Probably I cannot help your field because this might be the problem of the nature of nitrogen. The dinitrogen activation is rather hard thing among all the catalysis, I guess. So CO or CH or O or HH are very easily activated if we compare dinitrogen activation. So in order to activate the dinitrogen, that may be something special in the future. So in that case, I would say this might not be a good hint for the other area. So, but science is such a thing. So if you get into some wall in your research, you might think about something different field. At that time, you might help something.
Okay, I will learn a lot more about the catalyst. Thank you very much.
There any question? I have to say, in the final slide, you show the near future plant for ammonia synthesis. But in that plant, hydrogen and ammonia are synthesized separately. But so I want to know the possibility about the direct electrolysis for ammonia synthesis.
There are several groups who are trying to develop such kind of system. So I hope they should succeed. So one is to decompose water on their electrocatalysis, and at the same time, the hydrogen is used to reduce nitrogen at the same time. The problem is, if the best condition match well, that's okay. But I'm very much wondering the condition to decompose water is not a good condition to activate dinitrogen. But I don't deny the young people to overcome this problem. So that's a hard wall, but there may be some answer in the future.
Thank you very much.
Thank you very much. You're very stimulating lectures. But I'm the biologist, so I'm very simple question. You synthesized many the catalysts, and then but you didn't mention about
like the molybdenum or some vanadium of the catalyst. And also, I also don't know where about that area, but this kind of the dinitrogen hydrogen is why they use the kind of the metal. And that's first question. And second is that usually the dinitrogen activation, before the activation, in nature they use of the low potential electron, the donor is like the low potential paradoxine. So this kind of system, why you did not use in the catalyst research?
Okay, the first point is rather easy for me. Molybdenum and vanadium is usually, if we use those elements our condition of ammonia synthesis, those are completely turned to nitride. In the case of molybdenum 2N, that is a stabilized stable state of the catalyst. So the chemistry of nitride is a little bit different from iron and ruthenium. So there may be some possibility molybdenum or molybdenum as an industrial catalyst in the future, but the research is rather low. But one of the reasons maybe the molybdenum is not so abundant element. Molybdenum might be a little bit expensive element. So of course ruthenium is expensive, but we can use quite small amount of ruthenium as a support type. But molybdenum must be used as a element itself as an ion. So we must use molybdenum as a quite big amount in the reactor. So in that case, ion is better than molybdenum. But the chemistry of molybdenum nitride as a catalyst is very important for me. That is related with dinitrogen nitrogenase chemistry. So that is the answer for one. For the second answer, of course, our process, the dinitrogen rupture occurs first at some high temperature. But in biology system, dinitrogen itself gets electron one by one before break NN bond completely. So the system is quite goes quite slowly and very much well large steps exist in your system. So probably the speed, the temperature may be the most different factors. So we cannot keep hydrogen intermediate or imide intermediate is not observed at high temperature. So the reaction mechanism is a little bit different. So our system first occur dinitrogen rupture, then hydrogen attack one by one. So the system is a little bit different. So I cannot good comment for this. Thank you.
Are there any questions? Okay. Thank you so much. So let's thank Professor Aika. Thank you very much for your kind of